Hello, everyone. We have today's second lecture about zero-knowledge proofs. In the first lecture, we understand that zero-knowledge is the technology which allows us to prove a statement without revealing the statement itself. And now we will talk about what it means if we apply this rule to Ethereum virtual machine. So we are going to talk about zero-knowledge EVMs. By the way, don't forget to like our videos on YouTube. You will help us very much if you will do it. Thank you. So why do we need ZK zero-knowledge Ethereum virtual machine rollups? Maybe you know that today Ethereum itself is quite expensive blockchain. The block space is really expensive, so it costs a few dollars to send just a simple transaction. What is the solution that was on my first lecture about DeFi technology is that we might have so-called rollups. It means that we are going to build additional independent blockchain, but it's not completely independent. It's connected to the Ethereum in a way that all transactions are which are happening on this rollup, on this separate blockchain, are secured by the Ethereum blockchain. And how zero-knowledge technology will allow us to do it is by this ZK proofs. So actually, what ZK-EVMs, ZK-EVM rollups are doing, they're simply using this zero-knowledge proof to prove for the smart contract, which is deployed on the mainnet Ethereum, that everything what has happened in this ZK-EVM rollup is happened according to the rules of Ethereum virtual machine. So this is exactly what in other words, this is exactly the definition of zero-knowledge technology. So again, how do we use scalability? This is because we have batches of transactions. We have a few transactions which happen on our ZK-EVM rollup. Then we take these transactions, calculate zero-knowledge proof, send this proof to Ethereum mainnet contract, smart contract, and this smart contract checks this ZK proof and confirms that all that happened on our rollup happened according to the rules of Ethereum virtual machine. This is the scalability, and the privacy is that when you see these proofs and these transactions on this smart contract which sits on Ethereum mainnet, you will not understand what exact transactions happened in your ZK rollup. You might not need this functionality, but anyway, this is what exactly it looks like. So you simply see some proofs, but you cannot calculate what specific transaction happened on your ZK-EVM rollup from it. So to estimate the level of investment which go to the layer 2 technology, just look at it in the previous year, 2022 year. We had more than $1 billion investment in a few ZK rollups. So first of all, that's Polygon, ZK Sync, Starkware, and some others. So it's quite significant money going into development of this technology. What do we have in terms of solutions and rollups as a whole on which connected to the Ethereum and protected by Ethereum mainnet in terms of security in the way that I explained to you? So basically, we have two technologies. First, it's so-called optimistic technology. We're not gonna go deep into this, but the second one you see in this picture that the majority of all rollups are using ZK proofs. So it's quite popular technology. And let's go into the way exactly how can we distinguish one rollup from another. So what can we do with the ZK rollups on our on our EVMs. So on the two axes we have compatibility, that's the horizontal, that's the vertical one, and the performance of rollup, that's the horizontal one. By performance, I mean that actually the simplicity of calculating the proof. You might imagine that your rollup might have thousands, maybe hundreds of transactions per second, and you have to take this all transactions in one batch and calculate from these transactions, from this data, the proof according to the EVM rules. So it's quite calculation expensive and extensive task, and as close you go to the pure EVM standard, the more difficult to calculate this proof. And we see the first type of ZK-EVM, which is a complete copy or completely compatible to the original Ethereum ZK rollup. So it's, I would say, 100% compatible. That's the advantage. Simply, you can take transactions from the original Ethereum mainnet and send it to this type of rollup and get the same result. So these transactions will work, smart contracts will work as expected. So everything will be 100% compatible to what we have on Ethereum L1 or mainnet. But the other side of the coin is that it takes a very long time to generate proofs. So to resolve this problem, we go to the second type of ZK rollups, where we can verify environment, but we have minor changes in state tree, in so-called state tree. That means that it's still fully compatible, but it has, let's say, but it's takes a long time, but not so much to generate the proof. And we'll go through all of these types specifically in more details. And the last one, we have 2.5, 3, and the 4. It's where that's the fastest proof generation, but it's just compatible to the solidity on the language level, but it's not compatible on the base level of Ethereum and how it works. So let's get closer on each type. So the type 1, advantage, perfect compatibility. The disadvantage, that's the prover time. Again, to calculate proofs, to make it faster, you might even need so-called ZK snark ASICs. We've talked about ASICs, what ASICs is. They're used for mining Bitcoin, but there's different types of ASIC. Here we say that we need the special built computers, which only task is to calculate ZK proofs. So it's quite a computationally extensive task. Then going to the second, perfect equivalence at the virtual machine level. But with this ZK-EVM, we can still use the same smart contracts. We should not be afraid that something will not work, something will go wrong. But still, we have faster prover time than the type 1. But we might remove some code. We might use different hash functions. For example, for Ethereum, we use so-called KESAC hash function type. For this type of ZK-EVMs, for the second type, we might use Poseidon, which is another type. So it's modifications. It's different state tree of virtual machine, and we store different hashes. So remove some opcodes of the virtual machine. So it's not fully, still it's not 100% EVM equivalent. Speaking about the next type of ZK-EVM, we have 2.5. So here again, we try to save more calculation when we remove some, again, hash algorithms which are not compatible to zero-knowledge technologies. And what we have here, we have, and we approach to this by more gas costs for specific hash functions, which may reduce developer tooling compatibility and break a few applications. For example, if you try to hard code amount of gas in your smart contract, then that might be a problem, because if it works for Ethereum mainnet, Ethereum L1, it might not work for our type 2.5 EVM, because at some point you will need more gas, but you hard coded the lower amount, so that the function will be rewarded, the program will not work, your smart contract will not work. The third type, that's so-called almost EVM equivalent. So it's easy to build and faster proof times. So here we might calculate our proofs much faster, but we remove a few features that are exceptionally hard to implement, ZK-EVM, so-called precompiles, and a few others. And but what we have as a disadvantage, that's more incompatibility. It's not fully compatible with your Solidity smart code. So most applications will work, but some will require rewriting. What else? Some other tools for debugging might not work, and you have to actually be very cautious when you write something for type 3 ZK EVMs. And the last one, high-level language equivalent. Actually, how this ZK EVMs are built, we have the base layer, and it's completely different from what you have on the standard Ethereum virtual machine. But on the high-level language level, you have equivalent. It means that you might take your code, which the Solidity code for smart contracts, try to deploy it, but after you deploy it, it will be translated into other bytecode, which is different from bytecode. Is actually code which specifically implemented, or how to say it, actually played, I would say, by the Ethereum virtual machine. So here, very fast proof times, because your ZK-EVM is built from the standpoint that you take everything out which is difficult for ZK technology, so and replaced it for the tools which are ZK technology friendly. I mean, first of all, hash functions and some other stuff on Ethereum virtual machine. But normal application which you write on a Viper or Solidity can be compiled and just work. So it might happen that it will not work. And here a few types of contracts which will not work, and you need to write it in a different language. More than that, this type of ZK-EVMs might have their own specific smart contract language, which is different from the Solidity or Viper, which everyone get used to when they write Ethereum virtual machine applications, so-called decentralized applications. So now let's talk about specific projects. If you look on the right side, we have ZK-EVM smart rollups, which are completely compatible with Ethereum. So the scroll is the closest one. Today we have one more ZK-EVM rollup, which is ZK-EVM Polygon, which is not Hermes. And then we have Starknet, which is maybe 3 or 4 type ZK-EVM, and the ZK-Sync, which is the second one. So here you see that on the runtime level, which is the very base level of Ethereum virtual machine, we have ZK-EVM for scroll, U-EVM for Polygon Hermes, Zinc ZK-EVM, and Cairo ZK-EVM, which Cairo ZK-EVM, Zinc ZK-EVM, this is completely different from the original EVM. Then on the level of bytecode, which we already discussed what it is, that's the code which understands our Ethereum virtual machine. For the Starknet, we have Cairo assembly, which is not equal to the opcode used by Ethereum original. And the scroll and Polygon ZK-EVM, they use original opcodes used by Ethereum itself. And the language, you see here that for scroll, for Polygon Hermes, and for ZK-EVM Hermes, that's actually the same way as it goes with Ethereum. So you use Solidity and everything is okay. But for the Starknet, when you try to deploy the Solidity code on Starknet, actually it is translated into other language, readable Cairo language. If you know Cairo, you might write the programs directly in the Cairo. For ZK-Sync, it's also translated to a different language, and only after that, it compiled into bytecode, and only this completely different bytecode you deploy on your ZK-EVM virtual machine. So, say it in simple words, if you take bytecode from Starknet Cairo assembly, you will not be able to deploy it on EVM on Ethereum. But if you take opcode which you got from the scroll ZK-EVM, you might use it on original Ethereum. So they are completely compatible with a few maybe differences which are all documented, so you might understand what might go wrong. So that's pretty full list of ZK-EVMs which are already deployed. So now it's the second quarter of 2023. So we already have ZK-Sync, we have Starknet, we have Polygon, at least 3 of these Ethereum virtual machines which are built on ZK technology. You might use it already in a production environment. And if you go deeper into researching this ZK technology, ZK-EVM's rollups, you might see that maybe at some point ZK-Sync, maybe Starknet will have the Starknet, actually they have their own token, but for ZK-Sync you might have airdrop if you will be an early adopter, if you will use this EVM before the major distribution of their own governance token. But for the payment of gas fees, you see that on all ZK-EVMs, for exception of Starknet, you use real Ethereum. For the Starknet, because it's the 4th type of ZK-EVM, only partially compatible, they use their own token, and they have different type of addresses. It's much longer. So it's again it's bad for compatibility, but it's very good for calculation of the proofs. How ZK-EVMs work? So this is basically our circuit transaction processor. When we have the old root, old state of the system, then some transaction goes in this circuit, and then we have calculation the new root with the new proof and the new state of the system. If we go into more details, we say that we have transaction 1, transaction 2, transaction 3. We have the whole batch of this transaction and 3 transactions, and we go from old root to the new root. What happens in reality is that certain transactions are actually go into your ZK Ethereum virtual machine, then they're like going to blockchain, then maybe 10 minutes, maybe 30 minutes it takes to calculate the proof, and when this proof sent to the Ethereum mainnet, and accepted by the Ethereum smart contract, it means that this minus 30 minutes in time state is validated, so it's fine, so it's finalized. So it means that everything which happened in this before this time frame, before you calculated your proof and it was accepted by Ethereum, this transaction is okay, but in this what happened in this 30 minutes is not yet proved. So, and every ZK-EVM wants to actually decrease, to minimize this time. And the point is that it's quite hard to calculate this proof because it takes lots of efforts in terms of mathematical calculations. So now it takes more than, I think, 10 minutes. And the last topic for today is so-called private accounting systems or private blockchains, and we will talk about ZCash example. ZCash is one of the first ZK-based private blockchains, and if I'm not mistaken, it was launched maybe in 2016 or 2017. So it's quite a few years ago, and let's try to understand together how it works and where we need ZK technology for the system to work. So first of all, why we need privacy blockchains is the reason is very simple. When we look onto Bitcoin or Ethereum, we understand everything about the transaction. So we understand which address send what to which address. And if you calculate or somehow understand that the private key from this address belongs to a specific person, then you know all the history of transactions of this person. Some people do not want it and appeared the idea, let's build a blockchain which will allow to privately to send transactions. For ZK, for Zcash, we're not talking about the full Turing complete system, so it's not possible to implement smart contracts on Zcash, but it's possible to send native token from one address to another completely privately, meaning that looking from outside on the blockchain, you will not understand who sent to whom. So you do not understand the sender, you do not know the receiver, you do not know the amount which was sent. And not just you looking as outsider with the help of Blockchain Explorer, but even the nodes which supports the network, they will also do not understand what happened, who sent to whom and what. To understand how it works, let's imagine that this is, we start from the Bitcoin like system. Let's imagine that we have so-called nodes. It means that one Bitcoin and only one Bitcoin owned by a few addresses. And how can we record it on the blockchain? We can do it in a way that we say that public key 1, PK1, if we have it on blockchain, it means that PK1 owns one Bitcoin. PK2 also owns one Bitcoin. PK3 owns one Bitcoin. So in total, in our blockchain, we have 3 Bitcoins owned by the owner of public key first, public key second, and public key the third. So we start with this. Then if we want the transaction, so the change of ownership of one Bitcoin, let's imagine that Alice sends one Bitcoin to Bob. What we have on our blockchain, we have next state of our blockchain where PK1, public key 1, which is owned by Alice, does not own one Bitcoin anymore. but new private key 4 owns this Bitcoin. So this is exactly what happened. It means this new state that transaction happened and Bitcoin from PK1 went to PK4. Now let's make a first step to the privacy. And how we do it? We introduce so-called serial number. We just do it and that's it. Why we do it, I will explain in the next slide. Let's call it R small. And now we have this some random serial number, unique identifier of our one node of one Bitcoin. And now we define the node as private public key first, and this RR. So R1 public key first. Node 2 public key first, and R2. This means that actually the second Bitcoin is also owned by the same address, and so on. But in addition to that, we do not store these two values on blockchain, but we store the hash of this value. So we have H1, H2, and H3. So node 1, node 3, node 2, node 3. What it gives us is that the hash works in a way that knowing the hash, you cannot understand what was the original parameters with which this hash was calculated. So this is exactly how it works. So it means that already when you have this hashes of these nodes, you do not understand who is the owner of your coins on these blockchains. But in addition to that, we do not only store on our blockchain the owners of the nodes, which is at this moment and this state of the blockchain. But in addition to that, we actually, first of all, we store all nodes, all owners, all story of what happened on the blockchain. But we also store a so-called nullifier set. Nullifier set means that if we have it, this is the list of so-called spent coins. And this is the hash from this R, which we previously discussed. You see this serial number, unique identifier, the serial number. And it means that if we have an F1, which is the hash of R, this R second, it means that the second node was spent. It was sent to someone. It's not only unspent nodes, but the database of all nodes that ever existed with a nullifier set of the nodes which were spent sometimes in the past. And now let's imagine our private blockchain transaction, and Alice wants to send her coin to the Bob. Alice has node 1, Bob has public key 4. What happens? Alice randomly chooses a new serial number, R4. So it means that Alice needs to produce the nullifier because she is spending her coin. And what she also is doing, she defines node 4. So she is like producing with PK4 and R4 the new node which belongs to the Bob. So she knows the public key of the Bob. Then Alice sends node 4 to Bob privately. She has to send this data to Bob privately somehow. Don't discuss it, how it's done. The third step, Alice sends the nullifier set of node 1 to all nodes. So what the blockchain gets from Alice? In step 3, the blockchain receives the hash of R1. Everything who is looking in this transaction, nodes and the external observers, they do not understand that actually the first node was spent. They receive some hash, but they do not understand which exactly the transaction happened. And what in addition to that she's doing, she sends the hash of the new node to all nodes also, and she sends this H4 to the nodes. And we see our new state of the blockchain. Again, we have hashes. We added 2 hashes. We are as external observers, and the nodes do not understand which exactly node was spent, who are the sender, who are the addresser, who are the receiver of transactions. And when do we need the zero knowledge proof? Actually, we need zero knowledge proof. That's the whole point is here. Because we need to prove to the nodes that we can spend this specific node without revealing the data about ourselves. So that's the core of privacy. So we have to prove to the nodes of the system that we are able to spend our node, which is owned by public key 1, with the secret key 1 and with this random number 1, without actually revealing our public key, of course, our secret key in no way, and our identifier, unique identifier R1. So this is, and for this we need zero knowledge proofs, because without this technology, everyone can send some hashes to the system, try to spend nodes which are not belong to this address, and it will not work simply. But with zero knowledge proof, it works. So again, the hash of the node 1 PK1 R1 exists in a set of hash nodes. Secret key 1 is the private key corresponding to PK1, because it's not enough to prove that you have this PK1, but you have to prove that you can spend it. And how you do it on a blockchain, you have to prove that you know the secret key or private key, which corresponds to the specific public key. But our approach to the explanation is quite simplistic, even though you might think that it's complicated for you, but it's not everything. But in the real Zcash technology, it works even more in a complicated way. So the hash nodes need to be stored not just as a list, but as a Merkle tree. Merkle trees are used on all blockchains. You might Google this word and read more about it. It's very important technology. So it's stored not as a list, but as a Merkle tree. Merkle tree allows you to find your transaction in much faster way than just listing all list of some nodes or some data. The nullifier needs to be defined in a more complex way to ensure future privacy in relation to the sender. And we discussed that somehow sender Alice has to privately send information node 4 to the recipient. And we also have the technological solution for this problem. So we do not have this private channel between sender and the recipient of the transaction. This is the example of ZCash, so-called shielded or private transaction. So you see that the shielded is true. You do not understand who sent, which address sent, where the transaction was sent. You do not see the amount of the transaction. But Zcash allows you to send transactions which are completely public. So in this transaction, we see that the shielded is false. It means that the privacy is switched off. And this transaction is very similar to what we see on Ethereum or on Bitcoin. And we see the address, the sender address, inputs. We see the amount, free, ZEC, so it's Zcash currency, native currency, the coin. We see the recipient, and we see the recipient amount received. And we see the commission for this transaction. So we get all the data as on any public blockchain. So that's it for today. Thank you for your attention. If you have any questions, I'm ready to answer.
Okay. I don't have some question. Okay. Now I will add all materials, quiz for this topic, and the next meeting will be final, yes?
Yes, yes. The next lecture will be final, will be about so-called derivatives, options, futures, so-called that's actually a very interesting topic, and the very least, I would say, technology which are developing today on DeFi.
Yes, and after the next lecture, we will add all conditions for certification, and you will have final test for all topics, I think. And see you soon. Waiting for our updates.
Yeah, thank you for your attention.
Thank you. Bye-bye.
Bye.